Today we're going to talk about polynomial inequalities. And interestingly enough, this is not its own dedicated section in the textbook that we're using. Um, but we've been looking at polynomial graphs and equations, and it makes sense in a lot of applications to be able to solve polynomial inequalities. Before we dive into higher degree polynomial inequalities, I want to look at a quadratic, a linear, an absolute value. And I just want to, before we get into the steps on how to do this without a calculator, let's look at what we're doing using a graphing calculator so we can get the big picture. So use a graphing utility to find the solution set. It's not just going to be x equals this or this. It's going to be x can be anything between this number and this number um, to solve each inequality. And then we're going to sketch the graph just so we have it in our notes. And we will always answer in inequality notation. So for the first one, if I have a graphing calculator, there are two ways I can look at this. I can, in my y equals, I can type in, as I see it, 2x squared plus x. I can put that on one line and put 15 on the other. And so if we're going to solve that inequality with a graphing calculator, we could I'm just going to zoom 6 to see what it looks like. So I see the parabola. I don't see the 15 because this is going negative 10 to 10, but this kind of lets me adjust my window a bit. I'm good on the x values. I don't need to see negative 10 for the y values. Why don't we say maybe negative 2? And because we want to look for when the graph is greater than 15, maybe I'll have it go up to 30, just so I get a good picture, and then I'll just press graph. So what we're looking at, if we don't move anything, is when is the 2x squared plus x, when is the blue graph, greater than, or I can think of this as above, greater than 15. So if I'm looking on here, that's this branch to the right, this branch to the left. So let's sketch this graph. Just give yourself a little sketch. It doesn't have to be anything crazy. I'm going to show that I had a parabola of some sort. I'm not too worried about the details. Can't leave that like that. Something like this. And then there was the 15 line. And so what I'm looking at is these x values. Anything to the left of this point means that the parabola is above the line. And anything to the right of this x value, whatever it is, means the parabola is above the line. And the calculator can tell us what those values are if we just ask it to find an intersection point. So second, trace, intersect. And it just says first curve, second curve. So is it on the first curve? Yes, press enter. Is it on the second curve? Yes, press enter. Whatever point it's closer to is where it's going to jump. So 2.5 is that x value. And then if I find the other one, I do second, trace, intersect again. You do need to get your cursor closer to the other intersection point. So yes, I'm on the first curve, but I want to find this one. So I press enter. It hops straight up from there, so that's close enough. Enter. Enter a third time. So negative 3 is the other value. So my graphing utility helps me just by saying really quickly, when is this graph above this graph? Anytime in interval notation for any x value between negative infinity and negative 3. And it's just greater than, so let's not include negative 3 because that's where they're equal. Or any x value from 2.5 or 5 over 2 to infinity. We are going to learn how to solve these without a graphing calculator, but I just wanted you visually to see what we're doing. Another option is to say, we could have said when is 2x squared plus x, subtract the 15 over. When is that greater than 0? If we don't have a graphing calculator, we'll do this for sure. And so that would have done the same thing. I would have been looking for when is this graph above 0 or when is it above the x-axis. So I'll just show that kind of quickly. So let's say we subtracted 15. I'm going to zoom 6 again because I don't necessarily need such a huge thing. So when is this graph above the x-axis. Oops. I noticed something was wrong because my answers were not, they should still be -3 and 2.5, and they were not. I typed in a negative instead of a minus. Whoops. Makes a difference. There we go. So I get the same two answers, -3. Anything to the left of that is when the graph is above the x-axis, and 2.5, anything to the right of that. So you have that choice too. If I want to solve a double inequality in a graphing calculator, I can't like subtract both numbers at once. So instead, I would just do this. I would say, just line by line, I'm going to put, this is asking when is the line 2/5 x minus 4. For what x values does that fall between 3 and 7? So in here, if you put in 3 in one line, and then 2/5 x minus 4, and then 7. If we try to graph all three of these with zoom 6, we can just see if it fits. So far this is not fitting. Right now on this screen, the red line, the 2/5 x minus 4, is not falling between these. I've got some adjustments to make. Instead of just zoom out, zoom out, zoom out, just adjust your window. We definitely don't need x values in -10. Maybe I'll start at +10 and go out to like 30. And then for the y values, we're looking between 3 and 7. So I like to give a little buffer, but maybe instead of -10, I just bump it down to 2. And instead of 7, I bump it up to 8. And then I'll just press graph. So this is saying, when is the red line, the 2/5 x minus 4, when does it fall between the two horizontal lines 3 and 7? So I can see that on my screen. So if I want to sketch a visual, I've got the line 3, I've got the line 7, and then I've got some other line comes through like this. So we're saying, yeah, for whatever this x value is and whatever this x value is, this whole line here, that's my solution set. And then the calculator can tell me what those are. So second trace, intersect, first curve, yes, blue and red is one of the intersections I want to find. So 17.5. My scale's a bit off. I guess I don't need the y-axis in there. And then the other one, intersect. So I don't want the blue line this time. See how everything's in blue? I want to press up to hop to a different equation. So yes, the y = 7 line, press enter. And then no, not the blue. I want the red line. Is it going to let me get over there? There we go. I had to press up a few times to get to the red line. So even though my cursor's way down here, the blue and red only intersect over here. So that's okay. So 27.5. And again, for my sketch, I don't care about the scale. But for this one, we would say, let's see, we want to stay above 3, but not equal to 3. So I'm going to use parentheses, 17.5. And we want to be less than or equal to 7. So 27.5 gets included. And last one of these, we need to type in the absolute value of x squared minus 25. So I think absolute value is one of these alpha shortcuts. I just pressed alpha trace, and then you can just scroll left or right. There it is. So it would have been alpha window, I guess, to give me that. Or you can also just do math and arrow over once to number, and it's right there. Absolute value of x squared minus 25, and we wanted to know when that is greater than or equal to 10. So I'm going to zoom 6 again just to reset everything. So that absolute value graph is kind of cool. It's like this, you can't see the whole thing right now, but it's this weird little W shape. Let's get it so we can see the whole thing. Let's change the window. X min, maybe I'll take that to like -2, just so I can see the bottom. The max, well, we had that x squared minus 25, so maybe we'll bump this up to 30. And we're trying to get the line y = 10 in there. Oops, what happened? I changed the x values instead of the y values. Whoops. Okay, try that again. X was good at -10 and 10. Y needed to be negative. I wanted -2 to 30. Try this. There we go. So we've got this polynomial, weird looking like W-shaped graph. And then we're looking for when is the graph greater than or equal to or above. For this previous one, I should have written this. I think of this as between, greater than one number, but less than another. So this graph is above when let's sketch it. Give yourself the strange little W thing like that. Put the line y equals 10 going through there. So we're looking at anything to the left of this intersection, anything between these two values, and anything to the right of this intersection. That's where the W graph is above the line y equals 10. So we can find all those intersection points. Let's just see which one it finds first. 3.8729. Now this is going to be symmetric, right? So you don't really have to find 4 separate ones. If 3.873, we're going to round that to. If that's over here, then negative 3.873 will be over here. So this was 3.873, negative 3.873, and then let's just find the intersection over here on the right. So I'm going to scooch my graph over to that side, press enter, enter, 5.916, rounded to 3 places. So this one's going to be negative 5.916. All right, so answering in interval notation, this is greater than or equal to. So we do want to include these endpoints where it's equal to. We're going to say starting at negative infinity, you can go up to negative 5.916, close that off. Anything between negative 3.873 and positive 3.873. And then anything from 5.916 out to infinity. So if we have a graphing calculator, which we're likely to have for parts of our questions like this for parts of our calculator portion of our AP exam, then fine, this isn't too bad. It's just about being organized and getting a good window. But a lot of problems might ask us to solve without a calculator. So I try to write out some steps depending on what type of inequality we were going to solve. So the easiest ones are linear and double inequalities. So your whole goal for linear and double inequalities, you don't really need to graph it. Even though we did graph this linear double inequality, you don't necessarily have to graph it. It's nice to have that visual. But you can just start by isolating the input variable, which is usually, that just means get x by itself. Our AP test uses input variable often instead of independent or just x because it could be anything. If when you're isolating, if you end up multiplying or dividing both sides of the inequality by a negative value, then you've got to reverse the inequality after that step. So if it was a greater than problem, it'll switch to a less than. We'll see that as we do some of our work. And then whether or not that happened, you're just going to, once you isolate x, you're going to write your solution set in interval notation. So let's solve these first two without a calculator. Really, you can treat this like an equation. If I were solving this equation, I would first distribute the 7. 4t plus 8 is less than or equal to 7 plus 7t. I prefer to get my input variable, in this case t, on the left side of the inequality because I'm used to pointing left meaning less than and pointing right meaning greater than. So I'm going to do that. So I'm going to subtract 7t. That makes this negative 3t. And then subtract 8. Now subtracting does not change your inequality sign, but right here, when I divide by negative 3, that's going to flip that inequality symbol. So t is now greater than or equal to positive 1/3. Why does that happen? Why do we say you've got to flip if you divide by a negative? Well, the alternative is if I would have moved the t's to the right side, let's just show you this. I would have had this inequality. So I never had to divide by a negative, but see how it comes to the same conclusion? 1/3 is less than or equal to t, or t is greater than or equal to 1/3, I get the same thing. So if you move your independent variables so that you never have a negative coefficient, then you don't have to worry about that. But if you do have a negative coefficient, when you divide by that negative, you've got to switch your inequality because it makes the relationship the same. All right, so t is greater than or equal to 1/3. In interval notation, that's 1/3 to infinity. That's our solution set. If we were to graph this thing, we would say, when is the line on the left below the line on the right? And it would be for any t value 1/3 to infinity. If you have a double inequality that you're solving by hand rather than graphing, so when does 6x minus 1 fall between 11 and 23? When you isolate the x, the first step would be add 1. You're doing that to both sides. So now it's 12 is less than 6x, which is less than 24. When you divide by 6, that happens to both sides as well. 2 is less than x, which is less than 4. In interval notation, x is anything between 2 and 4. You can always verify these by graphing, by checking in your graphing calculator. There are more steps if we have an absolute value inequality. So I'm going to talk through these, but then our examples are on the next page. So actually, maybe I'll do a little bit of going back and forth. So first thing is to isolate the absolute value. So let's take a look at the first example and see if we need to do that. So yeah, in example number 6, isolate the absolute value means this plus 3 cannot be here when we go to step 2. So we're going to subtract 3 to the other side. So now it's the absolute value of x minus 5 is less than 2. So that's what I mean by isolate the absolute value. Remove the expression from within the absolute value to set up 2 inequalities. The first inequality keeps the inequality simple and keeps the expression to the right as is. So in our case, it's a number, but I said expression in case it's like x plus 2 or something. So what does that mean? That means here's your first inequality. Remove x minus 5 from the absolute value symbol and examine when is x minus 5 less than 2. Okay, because if I can come up with a value that calculates x minus 5 to be less than 2, it should work back in the original inequality. And we can solve that inequality. When is x less than 7? So as long as x is less than 7, when you take the absolute value of that number minus 5, you're going to get something less than 2. Okay, but we're not done there. Because if we look at, like, say 0, 0 is less than 7. But if I plug 0 back in here, the absolute value of 0 minus 5 is not less than 2. 5 is greater than 2. So there's got to be some other constraint. So here's the second inequality. The second inequality reverses the inequality symbol and multiplies the expression to the right by -1. So this says, what if x minus 5 is greater than, reverse the inequality symbol, instead of 2, -2. Solve that. If I add 5, I get 3. So I need to merge these two together. This says x can be less than 7, but greater than 3. So here's my third step to get my final answer here. Solve both inequalities and put them on a number line. So here's what we're looking at. This one says 7, anything to the left of 7. This one says 3, anything to the right of 3. If the original inequality is greater than, well, that's not us. If the original inequality is less than, the final solution set is only the overlapping shaded solution set. So only this section in here, what they had in common, is my solution set to this inequality. So let's write that down first. 3 to 7 is the answer. And why is that the case? Well, what I was saying earlier, what if I picked a number less than 7, like 0? If you check 0 back into the original inequality, you get something that's not true. 5 plus 3, 8, is not less than 5. So if I pick something between 3 and 7, like 4, if I put in 4 here, I get the absolute value of -1 plus 3. 1 plus 3 is less than 5 still. So anything between 3 and 7 will satisfy this inequality. The way I remember that is that less than is like less than, and meaning I want the overlap, if that helps you remember that. And then we'll look at some greater than problems and talk about that. So let's go through these steps again. For number 7, step 1 is isolate the absolute value. So get rid of this 2 that's being multiplied on the outside. You cannot distribute a 2 through an absolute value symbol. They're not like parentheses. So it's the absolute value of 2x plus 3 is greater than 8. And then we split 2x plus 3. We keep it greater than 8. And then there's the second inequality that says 2x plus 3 could also be less than negative 8. So I flipped the symbol, reversed the symbol, multiply the 8 by negative 1. Let's solve both of these inequalities. So the first one, if we subtract 3 and divide by 2, we get x is greater than 5 over 2, 2.5. For the second one, if we solve, when we subtract 3, we get negative 11. X is less than negative 11 over 2, or negative 5.5. Put these on a number line. So 5 over 2, anything greater than 5 over 2. Less than negative 11 over 2, so anything less than that. There is no overlap here, but this is where the second scenario comes into play. It's not that this is no solution, no overlap. This says if the original inequality is greater than, the final solution set is the total shaded area. So, excuse me. So for this one, I think great or, greater, or means this or that, total shading. You can also, if you're not sure, you don't have to just memorize these rules. You can also just test some numbers in between or in each solution set back into the original inequality and just see if it's true or false. Like if this is negative 5.5, put negative 6 in and see what happens. Or if this is 2.5, put 3 in or 4 or whatever and see if that checks out. If you're not sure about the middle part, plug in 0 and see if it works out. Is 2 times the absolute value of 3 greater than 16? No. So this solution set is negative infinity to negative 11 over 2 and 5 over 2 to infinity. Okay, number 8, isolate the absolute value, subtract 4. And if we set this up, we can say 3 minus x is less than negative 2. 3 minus x, flip the symbol, reverse the symbol, greater than, multiply that by negative 1, 2. Solve each part, subtract 3. Divide by negative 1, so that's going to flip this to x is greater than positive 5. On the other side, subtract 3. Again, divide by negative 1. That's going to make this x is now less than positive 1. Put those on a number line. Greater than 5. Less than 1. Here's where you have to pay attention. This was originally a less than problem. Less than, which means we want overlap. Is there any overlap? No overlap, so this is no solution. I could have saved myself a lot of trouble if I just paused for a minute. Back here, there's a connection between the problem and what our final solution was. An absolute value of whatever is always positive. Is there any way that a positive value, whatever it calculates out to be, will ever be less than a negative value? That's impossible. So it's no solution right off the bat before ever having to solve for all of this stuff. Okay, so I would like you to get in the habit of recognizing that. For the other two, is it possible for a positive number to be less than 2? Yeah, anything between 0 and 2 is less than 2. So that's possible we had to solve. Is it possible for a positive number to be bigger than 8? Yes, anything greater than 8 will be, any positive number bigger than 8 will be greater. And so, yeah, we had to take time to solve. But if you can pause and say, is it possible for a positive to be less than a negative? And just answer no solution, you don't have to show all of this work. Let's take a look at number 9. We have one more of these. First, divide by -3, and because you're doing that right off the bat, remember to reverse the symbol. This becomes the absolute value of x plus 4 is now greater than or equal to -3. Now, let's stop and pause on this one. Anytime I see a negative over here, I kind of stop and think. Greater means great or, right? And so we're not looking for an overlap, but we're saying, when is this positive number, can this positive number be greater than or equal to a negative number? Well, isn't it true that a positive number will always be bigger than a negative number? Or, well, I guess they won't be equal to each other, right? So yes, this is always true. So here's one where I don't have to do the overlap, or I don't have to look for the total shading. The total shading would be the entire number line. I'm just going to say -infinity to infinity. X is all real numbers. Okay, so save yourself some math by doing a quick check, especially if there's a negative on this side, and just see. Okay, polynomial inequalities. We were doing polynomial inequalities before. Linear lines are polynomials, right? Right, but when you start getting degree 2 or higher, you have to think about polynomial graphs. So these have a bit more, this is more of a structured rule set, not as much to memorize. First of all, I don't have the option like I did in example 1 of just leaving this greater than 15 and solving from there. Because remember, we can't factor and solve if something's not equal to 0. Excuse me, because there are too many options to set up. So instead, move all terms to one side of the inequality. I tend to move to the left side for the reasons I said before. It doesn't really matter. Now the inequality is being compared to 0. That means greater than 0 is like, when are you above the x-axis? Because we're going to be sketching graphs. Less than 0 is, when are you below the x-axis? And then you kind of temporarily set your polynomial expression equal to 0. Find the real zeros. If there are only imaginary zeros, it means we don't have x-intercepts. And then you can either sketch the polynomial graph using your end behavior rules and your multiplicity rules, or if you're kind of shaky on that, you're not quite sure, or you don't trust your rules and your graphing, I'll show you how to test numbers within each interval to figure out, is this a positive value or negative? And then depending on the problem, if it's greater than or less than, we figure out what our solution set is. Okay, so first one, get equal to 0 first. Compare to 0 first, I should say. So subtract 5. So we're going to find the zeros first. So this doesn't factor. So we need to figure out, when is x squared plus 3x minus 5? When is it just equal to 0? Let's start there. Quadratic formula. -3 plus or minus square root of 9 minus 4 times 1 times -5 all over 2 times 1. -3 plus or minus, so this is 9 plus 20, square root of 29 over 2. Okay, the next thing to do is to, so we found real zeros, sketch this graph. I know these zeros are weird, but this is just a quadratic, right? Quadratic, positive is some parabola that opens up. And even though they're strange zeros, we can see that this parabola that opens up like this, it hits the x-axis at -3 minus radical 29 all over 2. So the subtraction has to be further to the left. And -3 plus radical 29 over 2. It's got to be on the right. It'll always be like that. The subtraction is the left 0 and the addition is the right 0. And we're looking for, when is this graph above 0, greater than 0, above the x-axis? That's to the left and to the right of those zeros. Well, that's it. So our answer is -infinity to -3 minus radical 29 all over 2, and -3 plus radical 29 all over 2 to infinity. Number 11 is kind of nice because this is a polynomial. It's a degree 3, right? And it's important to know what would this be if I were to actually FOIL it out. I would get x cubed plus some other stuff. Remember, that's important if we're going to sketch this graph. This has already been factored for us. So we can find the zeros, x equals 3 and negative 4. We can put those zeros on a number line. Make sure you put them in the right order. Negative 4 is on the left, 3 is on the right. This problem is less than or equal to, so we're looking for when is the graph below the x-axis, and we can plot those two zeros. I probably should have back here, I probably should have used open circles to plot those, so I reminded myself not to fill in the ends. And then what does this graph look like? Remember, at 3, because you have a multiplicity of 2, the graph, for lack of a better word, bounces or does not change signs at 3. At negative 4, it's going to cross. The end behavior for an x cubed graph that's positive is up on the right, down on the left. So it's a very rough sketch. I do the end behavior first. I cross at negative 4. I bounce at 3. So take a look at what this graph is doing. The number line represents the x-axis, always. So the graph is negative on this section, or the graph is below the x-axis. It's positive between negative 4 and 3, and it's positive after 3. The question was, when is this graph less than or equal to 0? So less than 0 from negative infinity to negative 4, equal to 0 at negative 4, and don't forget about x equals 3. That's another value that makes this graph equal to 0. All right. If you didn't want to sketch that graph, we could test numbers. I'll show you in the next one how to test numbers. I'm still going to sketch the graph too, but I want to show you how to test numbers. So actually maybe not in this one, but x to the 4th plus 3. So this is already compared to 0. I can't factor that. If I try saying when is x to the 4th equal to negative 3, that answer's never, right? You can't 4th root something and get a negative answer, or you could also think of this as like, I might get imaginary numbers or something. So there are no real zeros, no x-intercepts. Think about this graph. X to the 4th is normally at 0, 0, and it opens up. Plus 3 means it starts up at 0, 3, and then it opens up from there. When is this graph less than 0? When is it below the x-axis? The answer is never. No solution. So if you can't find a real 0 and x-intercept, you need to think about whether you graph it or whether you just start plugging numbers in and seeing what kind of values you're getting. You can see, am I going to get positive values or negative values when I plug in whatever I can think of for x? Okay, what about 9 minus x squared greater than or equal to 0? So this one I can factor. 3 plus x, 3 minus x equals 0. X equals plus or minus 3. This one's quadratic. A negative x squared means when I sketch the graph, I'm going to be doing a parabola that opens down. I'm not sure why I'm drawing a y-axis there. So number line, negative 3, 3, greater than or equal to 0, so fill in those zeros. Sketch your parabola opening down like that. Again, the number line is the x-axis. So we're saying when is the graph above the x-axis? Anytime between negative 3 and 3. What if you wanted to test numbers? So if negative 3 and 3 are your x-intercepts, if you say you forget how to graph 9 minus x squared somehow, then you would plug in negative 4 into 9 minus x squared and see if it's coming out positive or negative. And then you would pick something between negative 3 and 3, like 0, and then pick 4. So this is negative, positive, negative. If you pick one number in that interval, because these are polynomial, any other number in that interval would come out to the same sign, positive or negative. And we want the positive section. So that's what I mean by test intervals. But we've been graphing polynomials for a while now, and you did it last year. It's faster usually to just graph, especially if it's a parabola. Okay, I can do the same thing for this next problem. I could just think of the graph. I could say, let's compare this to 0. Think of that graph. It's got a vertex at 2, -5, and then it's a parabola that opens up. When is it less than or equal to 0? In between whatever these two zeros are. Okay, so I've got to graph these two zeros. Now, what if you don't sketch that graph? All right, well, you can still figure out what the zeros are. You can say, let's go back to the original thing. You could square out x minus 2 squared into x squared minus 4x plus 4 minus 5, and then go from there. Or you could say, I'm going to square root both sides. Be careful though, when you square root x minus 2 squared, remember that's the absolute value of x minus 2. And then the plus or minus is generated because this is an absolute value function. So I would say if the absolute value of x minus 2 is less than or equal to radical 5, that means x minus 2 is less than or equal to radical 5, or x minus 2 is greater than or equal to negative radical 5. So x is less than or equal to 2 plus radical 5, or it's greater than or equal to 2 minus radical 5. This was an and, because it's an absolute value problem. So and, that means that we're looking for the overlap. Anything between 2 minus radical 5 and 2 plus radical 5. Like I said, if that was confusing, you could make this x squared minus 4x plus 4 minus 5 less than or equal to 0. Do quadratic formula, because this is going to be minus 1. Do quadratic formula like we did for number 10, and you'll get the same two zeros. Okay, last one. Get this equal to 0. Can this be factored? Don't just jump right into quadratic formula, especially if the numbers are kind of big. When we're finding zeros, we're just looking for equal 0. So 20 is probably going to get broken up into 5 and 4, right? And I know the 4 can't go with the 2, because then if it's 2x and 4, I would have been able to take a 2 out of the original. 5x and 8x, that's going to give me 3x if I make it positive 8x minus 5x. That checks out. So the zeros are 5 halves and -4. Toss those on a number line in the correct order. Less than or equal to means closed circles. This parabola opens up like that. We want less than or equal to. When is this thing below or negative? Below the x-axis or negative in this little chunk right here. -4 to 5/2. All right, I encourage you to sketch the graph, especially if it's quadratic. If it's polynomial, remember, if you're going to sketch the graph, you've got to really pay attention to end behavior and behavior at the zeros. But it all comes together. All right, that's it for today. If you have questions, please come to office hours or ask during class.